Hi, my name is Ashraf Takla, Mixel founder and CEO. Thanks for joining us here today. Our presentation is about using MIPI CSI2 and D-PHY for AI applications in IoT edge devices. We will start with a brief overview of the history of cloud and edge computing and the benefits and trade-offs between the two. Next, we will look at the perceived ergo and the system and the device block diagrams. We will then cover the problem that Perceive is addressing with their solution and their target applications. We will then cover why Perceive decided to use MIPI interfaces and why they selected FDSOI process for their design. We will wrap up with an overview of Mixel's MIPI IPs integrated into the Perceive chip and the silicon results. In recent years, we are seeing a trend toward edge processing closer to the source of the data. However, the history of data processing begins in the 60s and 70s with an on-site mainframes evolving to distributed client servers in the 80s. In the beginning of this century, centralized cloud processing became attractive, with cloud computing gaining momentum. It is only in the last several years that distributed edge computing becomes feasible and advantageous. You can see why we can call this back to the future. One of the original benefits of processing in the cloud in data centers was simply to expand beyond the limited capacity of on-site computing. With advancement in AI, more and more decisions can be made at the edge, and now it's clear that edge and cloud processing are complementary technologies. They are both essential to achieve optimal system performance. Designers of connected systems must ask, what is the most efficient system partitioning between the cloud and edge? Let us review the benefits of processing at the edge and then contrast that with the cloud. In most AI applications, quick response is essential. The ability to make decisions in real time with very low latency is mandatory. Edge computing plays a key role in meeting those demanding requirements and the high expectations of today's users. When you process data at the edge, you end up saving system power because less bandwidth is needed. You also minimize false notification, which also improves battery life. From security and privacy perspective, edge processing reduces the chance for breach while the raw data is in transit to be processed remotely. Of course, the local edge device needs to also be well protected and secured. In some locations, connecting to the cloud through broadband or cellular networks may not be possible, so local computing is mandatory. Even when the connection is available, cost might be a hurdle that can be addressed by deploying edge processing. Let us now review the benefit of cloud computing. The cloud offers massive computing power and large storage capacity that cannot be replicated at the edge. This is essential for complex machine learning and modeling, as because the cloud provides easy scalability that enables a system designer to expand storage and computing resources at incremental cost. Cloud resources are practically unlimited, and that is a huge advantage and very useful tool the system designer can rely on. Once the data is at the data center, the cloud provider can usually ensure high security and protection, although recent hacks put that theory to the test. Additionally, for maintenance and upgradability perspective, it is easier to upgrade one centralized location versus many endpoints. In this slide, we summarize the trade-offs between the two. Clearly, Each has benefits and some shortcomings, advantages and disadvantages. You simply cannot beat the processing power of data centers, but for the applications that require a real-time decision-making, Edge provides the lowest latency. Many modern AI-connected systems today require a mix of the two to maximize the benefits while mitigating the weaknesses. Now, let us turn our focus to the perceived Ergo. In edge devices supporting AI, you need a processor that is capable of machine learning. Perceive has done just that with the Ergo inference processor, which is designed for IoT and edge devices. It has 20 to 100 times the power efficiency of similar devices in the market and can deliver 4 sustained GPU equivalent terafloating point operations per second at 55 TOPS per watt. This horsepower can process large neural network using 20 milliwatt and support a variety of advanced neural networks, all at the edge. In this slide, we show how the Ergo can be integrated into a system for a typical AI application. The processor takes data from various sensors. On the left-hand side, you can see audio inputs via I2S, video input through MIPI CSI and CPI, and other information using I2C and I3C. In the middle of the slide, you see the processor with the NOR flash, which can be used for fast boot up. On the right-hand side sits the SoC, which receives both the perceptions and the raw audio and video data, which are used in tunneling applications. Let us now go over the Ergo block diagram. On the top left-hand corner, you see Ergo's built-in imaging interface section. This includes 2 MIPI and 2 CPI inputs and 1 MIPI output. It can support 2 simultaneous image processing pipelines, one high-performance 4K using 2 instances of the MIPI 4-lane D-PHY, and one standard high-definition using 1 instance. Moving down the bottom left-hand corner, you see Ergo's audio interface, which supports both mic inputs and a speaker output. Next, you see the CPU system in the bottom center. Its main function is chip management, data flow, communication with the processor. Some processing of audio is done by CPU subsystem, such as temporal to spectral conversion. The DSP engine does pre- and post-processing such as FFT. You can also see the Ergo's image processing unit in the top center, which processes raw images from the camera to make them more readily usable by the neural network fabric. It does functions like scaling, cropping, and color space conversion. The chip can perform inferences on images and video, and it can also offer the ability to tunnel video out through the MIPI transmitter. Tunneling is useful in many applications, such as security, where an alert can be accompanied by the corresponding audio and video. The Ergo then uses both audio and video or other sensor inputs to produce high-quality inferences. For example, motion detection, accompanied by the sound of breaking glass, might trigger a more trustworthy response in a security application. Let us now go to the brain of the Ergo. This is the neural network fabric you see in the top right-hand corner. The Ergo chip supports several neural network clusters, which allow it to simultaneously run multiple neural networks and support multiple input data types. For example, processing audio and video at the same time. The neural network clusters and their SRAM occupy over 2/3 of the area of the chip. This is where segmentation, identification, inferences, and other functions take place. Ergo is built to protect privacy and security without compromising speed, using an on-chip hardware accelerated decryption for the embedded software and neural assets. Perceive is targeting specific problems that edge devices are trying to solve. There are two main types of sensing, visual or audio. Each of these can be used to detect objects within the environment and recognize the user. Video object detection is used for home or enterprise security to detect interesting motion and ignore false alerts. Audio detection can detect critical sounds around the device to improve safety and contextual awareness. Face recognition can be used as a standalone biometric or part of a multi-factor authentication to unlock the device or objects. Speech recognition is used for wake-up words, device-specific commands, and natural language interfaces for smartphones, home appliances, and smart toys. Next, we will overview the different types of applications that the perceived device targets in some specific use cases. All the different applications use the same Ergo capabilities or a subset of them, so there is a lot of similarities. The way each one uses those capabilities is what differentiates each use case. Let's take a look at the smart home application, at a smart home application such as security cameras and doorbells. When using this processor for this kind of application, the system detects relevant motion and ignores false alerts, recognizes faces, voices, and people, detect relevant objects such as animals, packages, vehicles. It also uses voice for local command, detect important sounds such as alarms, people, glass breaking, etc. It can even describe the user, to the user people, vehicles, or the actions in the scene. Now, let us look at how the Ergo device sitting at the edge can be part of a home security system that also utilizes cloud computing. In such a system, you would have multiple cameras and potentially other sensors inside and outside the home. Those sensors can be monitoring movement, sounds, temperature, CO2 level, water leaks, entry point activities, and breaches. There is typically a cloud-connected local hub that all the edge devices connect to. Some of those edge devices can have an Ergo that processes data and uses AI to make local decisions. The hub gathers information from the different edge devices and uses local storage for some of the data and uploads some to the cloud. In the cloud, that data can be stored for long-term retention, can also be processed to improve existing algorithms or create new ones. This is where machine learning takes place, resulting, for example, in improved object and people identification and establishing better correlation between different events. For wearables, you can also detect important sounds around the user and use local voice commands and advanced wake-up words to simplify user interface. You can also recognize faces, voices, emotions, detect relevant objects around the user, and integrate data across multiple sensors. Now, let's take a look at how an Ergo built into a wearable device can be part of a connected system and what role the cloud would play in such an application. Here, multiple sensors would be built into the wearable device. Those sensors would be monitoring the surroundings. The Ergo AI engine will be processing the sensor's information and producing high-value inferences that can either be processed within the wearable or through a connected smart device. Through an internet connection, the wearable has access to the cloud where huge databases of information resides. Contacts, images, video, global maps, encyclopedias are all readily available. Relevant information can be projected for the user in some mixed reality environment through the microdisplay or projector into the wearable. Imagine you are walking or driving to a destination and you can see directions projected into your wearable. Or you are looking at an old acquaintance's face and the wearable automatically identifies the person and projects relevant information into the microdisplay. This can best be implemented using the processing power of the Ergo, the smartphone, and the cloud. This is the important and exciting role that the Ergo would play in next-generation wearables. The partitioning of the system between the wearable, the smartphone, and the cloud would determine the feasibility, practicality, and success of such a product. Next, let's take a brief look at how portable computing can use the Ergo capabilities. In addition to all the capabilities you already mentioned, the system can track eye location and interpret the user's emotion and attention using the built camera and smartphone. You can also blur or replace video conference background and improve audio and video quality. Looking at video conferencing devices, the Ergo is used in ways like those for portable computing, but can also support gesture or voice for touchless control. It can also be used to provide gaze correction and audience analytics. Now let's turn our attention to why was MIPI used in Ergo. Well, MIPI was designed from the ground up to minimize power while supporting high bandwidths and strict AMI requirements. Many edge applications are battery operated, so this fits in perfectly. MIPI CSI2 and D-PHY are both widely deployed for sensor application. The D-PHY is the first and most widely adopted MIPI in the market today. In this block diagram, we have a typical IoT device using MIPI CSI and PHY. You can see the D-PHY or C-PHY are used to support both camera and display applications. Why did Perceive choose an FDSOI process versus FinFET? Let's start by looking at the cross-section of a typical FDSOI transistor. Here, the channel is isolated for the bulk, which allows us to apply forward or reverse bias, resulting in the ability to control the transistor's threshold and leakage currents. Because of that and the inherently lower parasitics, FDSOI provides the right mix of features to achieve higher performance at lower power and lower cost without the need to move to the more costly FinFET processes. Compared to bulk silicon, FDSOI enables us to achieve higher performance and potential reduction in power and area because of the lower parasitic and back bias programmability. Body bias allows us to make trade-off between dynamic and leakage power to achieve lowest overall power consumption for a specific workload and operating conditions. For example, reverse body bias can be applied during standby mode to drastically reduce leakage current. FDSOI also enables performance and speed boost through forward body bias. It's no surprise that FDSOI is widely adopted in IoT devices. We conducted some analysis to quantify these benefits. In this evaluation, we applied forward bias to save area and reduce power. By doing so, we found that potential active area could be reduced by up to 55%, and the power could be reduced by up to 50% across PVT without any performance degradation. Let's now look at the Mixel MIPI PHYs integrated into the Ergo. We provided Perceive with MIPI receiver and transmit IPs, which were silicon proven in another FDSOI process before we ported them to 22FDX. On the receiver side, we delivered two different area-optimized receiver configurations of the CSI2 D-PHY, a 2-lane and a 4-lane versions. They both support MIPI D-PHY 2.1, which is backward compatible with V1.2 and V1.1. Both configurations run up to 2.5 gigabit per second per lane and support a low power mode running up to 80 megabit per second per lane. For the TX side, we provided Perceive an area-optimized 4-lane CSI2 D-PHY. This IP also supports MIPI D-PHY version 2.1 and has a high-speed transmit mode running at 2.5 gigabit per second per lane. This transmitter is used to support the tunneling function. Here you see eye diagrams of the TX IP running at 1.5 gigabit per second per lane and 2.5 gigabit per second per lane. Perceive achieved first-time success with the Mixel IPs and is now in production. Here is a quick overview of the Mixel silicon-proven IPs in two different FDSOI nodes and foundries. You can see a mix of D-PHY, transmitter, receiver, and universal lane configurations, together with LVDS and D-PHY LVDS combo IPs. All those IPs are silicon proven with first-time silicon success. For those of you who are not as familiar with Mixel, we are an industry leader in MIPI interfaces and a contributing member of the MIPI Alliance since 2006. We have a long track record with MIPI, with our MIPI D-PHY first silicon proven in 2008, MIPI M-PHY first silicon proven in 2011, and MIPI CSI first silicon proven in 2016. We offer a complete integrated solution, including the PHY, controller, and FPGA platform. We believe we have the widest coverage of process nodes and foundries for the MIPI PHYs. We are silicon proven in 11 different nodes and 8 different foundries. Let us now conclude by summarizing the presentation. Connected systems today need to strike a balance between cloud and edge processing to optimize system performance. MIPI specifications were specifically and uniquely developed to support low power, high bandwidth applications for mobile and edge devices. FDSOI is well suited for high performance applications at lower power and cost compared to FinFET technologies. This makes MIPI specification and FDSOI technologies a great match for edge devices. Processors like Perceive Ergo enable AI processing at the edge to make IoT devices smarter, achieve lower latency, and improve battery life and security. Mixel worked closely with Perceive SoC designers to leverage the benefit of MIPI in silicon-proven FDSOI IP, achieving the shortest path to first silicon success and high volume production. Many thanks to all of you for participating today.